Welcome to G Fun Facts Online. Today we are bypassing the usual pleasantries to take you directly into a vacuum chamber, roughly the size of a shoebox, located in a quiet laboratory at King's College London. Inside this chamber, suspended in absolute nothingness, is a speck of glass that is currently screaming. To the naked eye, this 5-micrometer silica sphere looks perfectly still. It is hovering, a ghost held in place not by strings or magnets, but by the invisible fingers of an oscillating electric field. If you were somehow able to touch this levitating bead, you would feel nothing unusual. It is room temperature. Its atoms are vibrating calmly at 300 Kelvin. But if you were to measure the motion of the sphere, the sheer violence with which it is thrashing against its invisible cage, and translate that kinetic energy into heat, your thermometer wouldn't just break. It would physically disintegrate. The reading would be 13 million Kelvin. That is the temperature of the deep stellar core. It is hot enough to fuse hydrogen into helium. It is a temperature that should instantly vaporize glass and strip electrons from nuclei. Yet, the glass bead remains solid, intact, and cool to the touch. This paradox is the heart of the levitated engine. To understand how a piece of glass can be colder than ice and hotter than the sun simultaneously, we have to rethink everything we know about engines. For centuries, thermodynamics has been the study of contact. Steam engines work because hot gas pushes against a piston. Car engines work because explosions drive a crankshaft. Energy is transferred by things touching other things. But contact is a thief. It steals energy through friction and leaks heat through conduction. To build the ultimate thermodynamic system, you must sever the connection to the physical world. You must levitate. The device used to achieve this 13 million degree state is called a Paul trap. Imagine a saddle. If you place a ball in the middle of a saddle, it will roll off to the sides. But if you spin that saddle fast enough, the ball gets trapped. Every time it tries to roll downhill, the surface spins and pushes it back up. The Paul trap does this with electric fields, creating a dynamic sweet spot where a charged glass nanosphere can float indefinitely. In the experiment at King's College led by Dr. James Millen, the air is pumped out until the pressure is a billionth of an atmosphere. At this level of vacuum, the sphere is effectively alone in the universe. It collides with a stray air molecule perhaps once every few milliseconds. This isolation is the secret. In a normal engine, the heat of the burning fuel transfers to the engine block. Everything equilibrates. But in the levitated engine, the body is the internal crystal lattice of the glass, and the working fluid is the movement of the sphere itself. Because there is no air to transfer heat between the two, they can exist at wildly different temperatures. The researchers injected chaos into this system by adding a noisy, random electrical signal to the trap. This noise acted like a heat bath, kicking the sphere randomly in all directions. The sphere responded by jittering into a frenzy. By carefully tuning this noise, they drove the motion of the sphere to a kinetic energy equivalent to 13 million Kelvin. The bead became a schizophrenic object, a solid, cool piece of glass possessing the violent movement of a fusion plasma. So why do we call this an engine? In classical physics, a heat engine takes thermal energy, converts some to work, and dumps the rest. The efficiency is strictly limited by the Carnot limit. But the levitated sphere is a stochastic heat engine. It is an engine made of probability. In this microscopic realm, the hot reservoir is the electrical noise making the particle jitter. The cold reservoir is the damping force trying to slow it down. The work is the energy the particle gives up as it moves against the electric fields. What makes this fascinating is that at this scale, the engine operates on fluctuations. A V8 engine averages out trillions of molecular collisions. But for the levitated nanosphere, every single kick matters. At 13 million Kelvin, the sphere enters a regime known as active matter. It behaves less like a passive rock and more like a living thing. Researchers found that by modulating the trap, squeezing and relaxing the electric field, they could extract work from this chaotic motion, forming a thermodynamic cycle just like a diesel engine. However, this engine does things that seem like magic. For brief moments, the levitated engine can appear to exceed the Carnot efficiency limit. It doesn't actually break the laws of physics, but it exploits the statistical nature of the second law. The second law says entropy increases statistically. For a steam engine, the odds of entropy decreasing are 0. For a single nanoparticle, the odds are small but real. The levitated engine can occasionally get lucky, borrowing energy from thermal fluctuations to perform more work than it technically should, provided it pays the debt back later. It also experiences negative friction. Instead of the environment slowing it down, the noise pumps energy into it, accelerating it further. This is how the temperature skyrockets. While this 5-micron bead is a marvel of theory, it has a massive cousin in the world of nuclear fusion, the Levitated Dipole Experiment, or LDX. If the glass bead is a study in thermodynamics, the LDX is a study in survival. Traditional fusion reactors like the tokamak use magnets wrapped around a donut-shaped chamber to hold plasma, but nature holds high-energy particles using dipoles, like the magnetic fields of Earth or Jupiter. A team from MIT and Columbia asked, what if we built a fusion reactor that looked like a planet? To do this, they needed a magnet inside the plasma, but you can't have supports holding the magnet up, because they would melt in the fusion fire. The solution was to levitate the reactor core. The LDX features a half-ton, donut-shaped superconducting magnet made of niobium tin. Before the experiment, this magnet is cooled to 4 Kelvin. It is then energized, creating a massive magnetic field. Then, the supports are withdrawn. A second magnet on top catches the donut, lifting it into the air. The result is a half-ton superconductor floating freely inside a vacuum chamber. Surrounding this floating ring, researchers inject gas and heat it to millions of degrees into plasma. Here, the levitated engine concept scales up. The floating magnet is thermally isolated. It is a 4 Kelvin object floating inside a millions of Kelvin hellscape. If it touches anything, the experiment ends. The LDX demonstrated a phenomenon called turbulent pinching. Usually, turbulence is bad for reactors. It makes plasma leak. But in the levitated dipole, turbulence actually packs the plasma tighter, increasing density near the core. It works like a thermodynamic pump, naturally organizing the chaos. Let's return to the microscopic scale. The 13 million degree glass bead is part of a broader revolution called active matter. Passive matter is a rock rolling down a hill. Gravity pulls it. Active matter is a bird flying or a bacteria swimming. It burns energy to generate force. The levitated engine is a simulator for active matter. By programming the electrical noise, researchers can make the glass bead behave like a frantic bacterium. This is crucial because biology is essentially a heat engine that ignores the rules we are used to. Inside your cells, protein motors called kinesin walk along structure highways hauling cargo. They operate in a thermal storm. To a kinesin molecule, the water molecules surrounding it are bombarding it like cannonballs. It should NT be able to walk straight, yet it uses that random thermal noise to its advantage, rectifying chaos into directed motion. This is called a Brownian ratchet. The 13 million degree experiment allows physicists to study this rectification at extreme limits. It raises the question, can we build a computer that runs on heat noise? Conventional computers fight heat, it's the enemy. But thermodynamic computing suggests we could build logic gates that use thermal fluctuations to flip bits, guiding the noise rather than fighting it. But here is the most ironic twist in this story. To truly understand this heat, we must freeze it to zero. The 13 million Kelvin figure is a measure of center of mass energy, but researchers are also doing the exact opposite. This is the field of cavity optomechanics. Instead of using electric fields to shake the particle, they use lasers to slow it down. When a laser beam hits a glass bead, it exerts radiation pressure. By carefully tuning the laser, you can create an optical tweezer. If the bead tries to move left, the laser pushes it right. If you do this with a feedback loop, you apply a friction that doesn't exist in nature. You drain the kinetic energy out of the bead. In recent years, teams in Vienna and Zurich have managed to cool the motion of a levitated nanosphere down to the quantum ground state. This is a temperature of almost absolute zero. At this state, the bead stops behaving like a classical object and starts behaving like a quantum wave. The engine stops running. This creates a bridge between two worlds. We can take a particle, cool it to the quantum ground state, and then suddenly hit it with the 13 million degree noise sequence. We can watch, in real time, how a quantum system becomes a classical thermodynamic system. We can watch the birth of heat. This is the stage where the transition from the smooth, reversible world of quantum mechanics to the messy, irreversible world of thermodynamics plays out. The technology of levitated thermodynamics is moving from curiosity to utility. First, we have the dark matter detector. A particle levitated in a vacuum has almost zero friction. If a stray wave of dark matter, the invisible substance making up most of the universe, were to nudge it, the sphere would recoil. Researchers are designing levitated arrays to listen for the wind of dark matter. Second, navigation. A levitated spinning nanosphere can rotate at millions of RPM with no friction. It is a gyroscope that never drifts, potentially allowing for navigation without GPS. Third, energy harvesting. Imagine a device floating inside a hot exhaust pipe, converting the thermal noise of the gas directly into electricity without ever touching the walls. Finally, the levitated engine challenges our philosophy of machines. We are creatures of contact. We touch, push, and burn. Our engines are brutalist machines of steel, but the universe is mostly empty space. The natural state of matter is isolation. The experiment at King's College teaches us that temperature is not just a number, but a story about how energy is distributed. It teaches us that an engine doesn't need pistons. It can be a probability distribution, a song of electrical noise played to a lonely sphere in the dark. It is the hottest object in the room, yet it cannot burn you. It is a solid that flows like plasma. As we look at that vibrating speck of glass, we are looking at the future of machines. Machines lighter than air, hotter than stars, and powered by the noise of existence itself. Thanks for listening to G Fun Facts Online.